Okay, morning everyone. Another video from me. This time we're going to look at the Arrhenius equation. Now, the Arrhenius equation involves going through some fairly complex maths. And it was, I must confess, a topic which I considered just not doing remotely for now and waiting till we got back to class. But then I just rethought, I thought, wait a minute, actually, for two reasons it's worth having a go now. One, actually, with complex concepts like this, it can almost work out better to learn it through a video tutorial, because it gives you the chance to sort of pause the explanation when you need to, stop and think about what I've just said, continue when you're satisfied with it, and you don't get that chance in class. You can't just pause me when I'm in the front of the class. So it might almost be better to do it this way, actually, I think. And secondly, we'll have a review of it in class anyway. We will give you another chance to go through this in class come September. It's just, I think it's really worth you having tried it at home first, so by the time you come to do it in class, you've already at least had some practice and some introduction to what all this means, and it's not too much to take in at once. Okay, so let's plunge in and go for it. Well, let's start with a quick look at the equation itself. Copying or just filming really here the Chem Guide webpage. I'll send you a link to this in the email as well. This is the Arrhenius equation itself. You can see various components all listed here. K, the rate constant, we're familiar with that. This equation was devised, by the way, by a Swedish chemist called Svante Arrhenius, who was really looking at the activation energy for reactions and looking at a way that we could find an expression which allowed us to calculate activation energy. Now, rate constant K will equal something called A, the pre-exponential factor, times E. We know what E is by now, 2.72, but E is raised to the power of minus the activation energy over R, the gas constant, we've met that before, 8.31, times the temperature in Kelvin. So that's already a fairly complex equation. However, in this form, it's not really usable. We need to make it more useful to us. We need to rearrange that equation, and I'm going to explain to you how to do that now. Right, now really I'm going to do two things with this Arrhenius equation. One, I'm going to rearrange the equation into a useful form and justify each step of that rearrangement process in the hope that you gain a full understanding of why this rearrangement is valid and why it makes it more useful to us. Secondly, I'm then going to explain how to use the rearranged version of the Arrhenius equation in order to calculate two things, the activation energy and the value of A. They're the two things that you have to be able to calculate for your syllabus. Now, strictly for your exams, you actually only need to be able to follow the second part of what I'm going to say, the part that is explaining how to calculate activation energy and the value of A. You don't really essentially need to understand why the rearrangement of the equation is valid. It's just that I'm not really in favour of just presenting you with a rearranged equation and say, go ahead and use this with you, when you don't really understand why it works or why the equation is valid. I'm not really a fan of students just saying that. I much prefer you to try to have a full understanding of why what you're doing is valid. But when I go through the rearrangement process, and I'll go through it as slowly and carefully as I can, if at any point you start to get a little bit lost or confused, do at least comfort yourself that actually for a chemistry exam question, I will never actually need to understand this. It's only the second part that you really need to be able to follow. But actually, if we take it step by step, what I'm going to go through is not too complicated. Right, so this Arrhenius equation, as I said, in its current form is not terribly useful. When we use it principally to calculate the value of activation energy. When we calculate the value of activation energy, we use the expression which you learnt about in the previous exercise, y equals mx plus c, because we use the gradient of a graph, in other words m, to calculate the activation energy. Therefore, we've somehow got to rearrange this equation and write it in the format of y equals mx plus c. And that's what I'm going to take you through now, how we can rearrange this equation and get it in the format of y equals mx plus c. Right, now the first step of the rearrangement process is just to take the natural log, or the ln of both sides. We've learned in the previous exercise what ln means. So if I just put ln of k and make this side ln of a times e to the minus e over rt, got that. However, whilst this side is fine, just being ln k, this is still a bit of a handful. Ln of a times e minus e over rt. We want to try to sort of simplify this or rearrange it. So how do we go about doing that? Well, what we've got is the natural log of one number times another number, because in the end e to the power minus e over rt could be brought as a single number. So let's look at how we do natural logs of two numbers multiplied together. Ln of 10 times 5. Or get your calculator out if you haven't done so already and work out the value of that. In other words, what's the ln of 50? Well, simple enough, 3.91. Next thing we want you to do, what is the ln of 10 plus the ln of 5 worked out separately and then add together? Try that. Right, again, nothing too difficult so far. Ln of 10 is 2.3, ln of 5 is 1.61. So you get the same answer, 3.91. In other words, ln of 10 times 5 is the same as the ln of 10 plus the ln of 5. So we can use that to rearrange this top part as well as follows. In other words, because the ln of 10 times 5 is the same as ln 10 plus ln 5, the ln of a times e is the same as ln of a plus the ln of e to the power. Okay. Well, next exercise. Quickly work out the value of e cubed and e to the minus 2. Right, we did this in the math skill exercise, but just a quick reminder anyway. To get e, you go shift ln, and you'll get e up, then you can put whatever power you want. So if you want it cubed, you go like that, equals, and there's your answer, 20.1. Let's go to 3 sig figs. Do the same for e to the minus 2, and you should get these two answers easily enough. Okay, let's move on again. Right, now let's do things the other way around. Work out the ln of 20.1 and the ln of 0.135, working out the ln of our answers. Lo and behold, the ln of 20.1 is 3 and 0.135 is minus 2. So, hopefully you can quickly see a pattern here. I'm only really reminding you of a pattern that you should have already learnt in the previous exercise. So, if e to the power 3 is 20.1, the ln of 20.1 is 3. In other words, the ln of a number is the power to which e must be raised to equal that number. Now, why are we doing all this? We're doing it because we want to simplify this part of this expression, which is still a bit of a handful. So let's just go a step further. What is the ln of e cubed? And whilst you're at it, work out the ln of e to the minus 2 as well. Right, again, just show you how to do it on the calculator in case you're not sure. Let's get you for ln of e cubed, you press ln, then you've got to go shift ln to get e, and just put 3. So you've got that on your screen, equals, the answer is indeed 3. And the same happens with minus 2. So if you do ln and e, sort of cancel each other out, really, don't they? And you end up with just the power to which e was raised as your answer. The ln of e to any power is just that power. So wait a minute, that means we can rearrange this part of our expression, can't we? ln of e to the minus eo over rt is actually just, you should be able to write that in for yourselves. We just remove both the ln and the e, and we've got that. It actually equals minus ea over rt. Right, at this point, let's have a quick recap of why we're doing all of this. Remember, we're rearranging this Arrhenius equation into a more useful form. First thing we did was take the natural log of both sides, but we'd already established that ln of a times e can be rewritten as ln of a plus ln of e. But we can now simplify this part of the expression. You've got an ln and an e, they cancel each other out, and you are basically left with this on this side. So we've now got our right hand side reading ln a minus ea over r times t. We still want to make a couple of slight further readjustments that we're still not finished yet in making it into a more useful form. The first readjustment is very simple though. ln k equals ln a minus ea over rt. You know, minus ea over rt could be, of course, just calculated to find a single number. I could put simple numbers into such an expression and say, well, what if 8 equals 10 times 2? That's the case. I can rearrange that and say, well, if I wanted to shift this here, which we do, we want to shift the ea over rt to this position, just makes it a bit easier to use for reasons you'll see in a minute. I could just as easily write that as 8 equals minus 2 plus 10, and therefore I could just as easily write ln a minus ea over rt as that, because, you know, I'm just shifting this to that position there, the minus 2 to that position. You know, this is the equivalent of the minus 2. I just shift it to there. And now we're almost done with rearranging this expression. Right, here's a summary of what we've done so far. We just took the ln of both sides. We said, well, that is the same as that. And I can cancel out the ln and the e and make it into that, and then I can shift that to this position and make it this. So far we've got to this, but we're not quite done. The whole purpose of this exercise was to get this Arrhenius equation in the form y equals mx plus c. Now ln k can be our y value, plus ln a, well, the ln a is the equivalent of c. We haven't really got this in the format mx. For this, it needs to be something times something on this side. So we've got one final adjustment to make. We need to take this part of the expression and convert it into the form mx. So let's just write out an equivalent expression here. Right, place of ea, I'll put at, and this bottom is r times t, so it's r4 and t is 5. Let's just say, I know r is strictly a constant 8.31, but let's assume it's 4 for now, and let's just not bother putting the minus number in, which just gets in the way. Now 80 over 4 times 5. Shame on you if you need a calculator to answer that, by the way. Work it out quickly. So we basically got 80 over 20, but could I rewrite that? Yes, I can. 80 over 4 times 5 could be rewritten as 80 over 4 times 1 over 5. It'll still come up with the same answer. Double check it if you like. 80 over 4 equals 20 times a fifth. Fifth of 20 is 4. So we can now go ahead and do our final step and do a similar rearrangement with that minus EA over RT. Right, if 80 over 4 times 5 could be rewritten as 80 over 4 times 1 over 5, then minus EA over R times T could be rewritten as minus EA over R times 1 over T. With that, we can therefore rewrite the Arrhenius equation as this, and lo and behold, you then got it in the format you want. lnk is y minus EA over R is m times 1 over, well, because it's times 1 over t, 1 over t is x, and lna is in the C position. That means we can now go ahead and plot a graph with lnk on our y-axis, 1 over t. Remember, this is capital T temperature, 1 over temperature on our x-axis. And if we calculate the gradient of that graph, m, the gradient will equal minus the activation energy over r. And given that r is a fixed constant of 8.31, if we've calculated the value of m, all we have to do is, if m equals minus EA over r, we can easily convert that m value into an activation energy. Right, so that's the first part of what I wanted to explain done. Remember what I said earlier, actually everything that I've covered up to now strictly does not need, definitely doesn't need to be recorded for an exam. You'll never be asked in a chemistry exam justify why the Arrhenius equation like this can be rewritten in this form and therefore have y equals mx plus c apply to it. No, you won't. I just wanted you to understand why what our rearrangement is valid and helpful. It gives you a much better understanding of what you're doing. What I'm explaining from now on, how to use this rearranged expression to calculate the value of EA and to calculate the value of A, you do need to know for a chemistry exam. Right, in a chemistry exam question, you might get a table like this, and you'll be able to do several things. 1, complete the table. 2, plot a graph. 3, use your graph to calculate the value of activation energy, and 4th, use your graph to calculate the value of A. So let's go through those step by step. Complete the table to begin with. This column is easy enough. Do 1 over 2, so that's just 1 divided by 280 and so on. You can fill that in. ln of k. Remember, k is the rate constant. This would be, some experimental figures that were devised. People would have to have done experiments to have got these. They've done a certain reaction, could be any reaction really, at 5 different temperatures. If you carry out the same reaction with the same chemicals at the same concentrations at a range of different temperatures, you can use your results to work out the activation energy. First thing you'd have to do is work out the value of K from your results. But if you know the rate equation for the reaction is something like that, and you know the concentration of A and B that you've used, and in your experiment you work out the rate of reaction, your results enable you to calculate the rate. You know the rate, you know A, you know B, you can work out the value of K from your results. Of course, you can just rearrange, of course, the expression like that. You've already learned and work out the value of K is enough. So anyway, you've got these results. You'd have to do the ln of each of these K values. Since you calculate, literally put ln of 3.8 times 10 to the minus 6. Right, just copy and complete this table. Useful first bit of practice for you, or pause the video. Right, hopefully you've come up with these figures. We've now got to go about plotting it on a graph. As mentioned earlier, lnk goes on the y-axis and 1 over temperature goes on the x-axis. So, a couple of things to point out. It can seem a bit awkward at first, plotting such tiny numbers on an x-axis, but there's an easy way around that. Just label your x-axis 1 over t times 10 to the minus 3. Do put the units k, that's a capital K, to the minus 1. You can end up with room for confusion. You've got a capital K for Kelvin, then you've got a lowercase k for rate constant here, so just be clear about which is which. Now, anyway, more importantly, scaling your axis, because your figures basically only go from 3.1 so up to about 3.6. You can scale your axes like that. And is it okay to just do your axes like that in chemistry with one of these silly squiggly little lines? No, it certainly is not okay. In fact, that's a shootable offence, so we don't want any of that. That is what our x-axis looks like. Now, sorry if everything in that was me banging on the desk actually, rearranging things. Anyway, our y-axis, they're easier to handle, but they are negative numbers, which means our y-axis has to really look like that. It's actually sort of coming down below the x-axis. Again, no need to start it at 0, and certainly no silly squiggly lines. You can plot it from range -7 to -13, and you can then plot each of those points on the graph. And I've duly plotted the points there. What you then always do on these graphs is join them with a straight line of best fit. That does not mean, by the way, as I see some fools do, just drawing a line from the first point to the last point. You want to arrange your lines so it's as close as possible to as many points as possible, unless you just consider that point to be really anomalous. Right. I've managed to come up with that and get 3 points on the line, one just below it, one just above it. You'll always be given a slight bit of leeway as to how you draw your line anyway, so I know it's a little bit subjective. Anyway, you do that line, then work out the gradient of the line. So, I've drawn a triangle on my graph. When doing a triangle for your gradient, you can draw it anywhere. Try to at least make one of the two sides of the triangle a nice round number. Now, notice how I've just done this so that this one is at least just comes to 0.1. Strictly, that's 0.1 times 10 to the minus 3. Don't forget that when calculating your grade. It's absolutely vital. If you label this times 10 to the minus 3, you must then carry that down. This one has gone down by minus 1.2. It's a negative gradient. It's going this way. You know, we'd only have a positive gradient if the line was going that way. It's gone from about minus 8.05 to minus 9.25. And therefore, I've calculated my gradient to be that. Now, quickly back to y equals mx plus c. We'd already learnt that our gradient m equals minus ea over r. So, if minus ea over r equals the gradient, as shown there, if we want to make ea the subject of that expression, well, I could firstly just move the minus ea over and say it's the gradient times r. Then, just to remove the minus sign from this, I'll move it over to the other side, and ea becomes minus gradient times r. Now, given that our gradient is itself minus 12,000, if our ea is minus gradient over r, it becomes ea is minus 12,000, and the two minuses cancel each other out, and it just ends up becoming back into a positive number times 8.31. Gradients of these graphs always come out as negative figures. They've always got a negative slope. But because in this expression we put minus gradient, you always end up removing the minus number at this stage anyway and coming up with a positive number. 99,720 joules, that is the value for the activation energy. If you're asking about it into kilojoules, 99.7. Okay, that's the activation energy done. One last thing, how to calculate the value of A. Now, as we've already said, we'd rewritten this expression in the format y equals mx plus c. ln A is in the C position. And remember, as we previously learned, you can get the value of C from the y-intercept on the graph here. The y-intercept was 1, so C equals 1 and y equals 2x plus 1. Do you remember the gradient of this one was 2, so m is 2 and C is 1. Now, we've used our m gradient to work out the value of the EA. We can just use the y-intercept to get the value of ln A. That's all nice and easy. Oh dear, wait a minute, it's not quite so easy, is it? For starters, we don't have a y-intercept. You'd say, oh well, you just need to have rescaled your graph, don't you, and just gone up a few more negative numbers here, and you could have got that to cross the x-axis at maybe about minus 5.5, and we could use that, but actually we still couldn't use that even if we had done it. So let's just show you exactly the type of thing I was referring to, actually drawing it out. Let's just say I'd scaled my y-axis like this and allowed for a bit of extra room. I could have found out a y-intercept, and therefore I could say ln A is minus 5.7. That'd be wrong. Why? Because why? Well, because it's not a true y-intercept, that value. Here is a genuine y-intercept is 1 because it is where the y-axis is drawn where x equals 0. Trouble with my graph is I have not drawn my y-axis from the point at which x equals 0. I've actually got x equals 3, strictly it's 3 times 10 to the minus 3. Now you could say, well, should you have redrawn your x-axis as well then? Going back to the original graph, to have drawn the x-axis to have incorporated 0, when I've got the scale going up just in 0.1, so I'd have had to go to 2.9, 2.8, I'd have needed a piece of graph paper as long as my arm, or I condense the scale right down. Now, the trouble with doing that is I'd end up with a load of wasted space on my graph, really, if I tried to scale it. When all the points are between 3 and 4, to have all this wasted space would mean I wouldn't actually be able to plot these points so accurately. And there's all this wasted space, and even then, actually I still don't easily get a y-intercept. I'd have to have carried this scale up massively and somehow have a y-intercept that somehow, again, I'd still need an enormous piece of graph paper. If I were trying to position that roughly along my points, I'd need a graph paper going up to there. So in practice, it's actually not practical in most of these graphs to get a y-intercept, so we work out A in a different way. Right, I showed you earlier all these sort of steps of rearranging this Arrhenius equation to get down to this, and we went through all these steps on the way. Now, to work out the value of A, we need to make ln A the subject of the equation. We can use this final form if we want, but actually it's easier to take a couple of steps back and use this version of it to work out the value of ln A. It's just much easier to rearrange this one and make ln A the subject of that equation. And by the way, this is a copy of the data sheet you're given in the exam. You don't have to remember these equations. You're given the original Arrhenius equation, but it's not really of any use to you in that format. You are given this as well, and you're given the value of R. Good to see. And this here is, of course, the same as that. In fact, what it's exactly the same. The version you're given is this form of it. Now, if ln k is ln A minus EA over RT, it's easy enough to rearrange that and just make ln A equal to ln k plus EA over RT. And really then, it's just a matter of inputting values. The activation energy you've already calculated. R is 8.31, it's a fixed number, and ln k and T could in theory be obtained from any row of this table, and in theory it shouldn't matter which row you use. You could just say, well, let's use 300 and minus 9.6 and put them in there. Actually, in practice, it's best to look back at your graph and choose one of the points that was right on the line of best fit, or at least closest to it, if not all on it. So I'll choose this middle one, which means choosing a value of 300 for T and minus 9.6 for ln k. So here we are, I've rewritten it like this. I've used 9.6 as ln k. I'd previously calculated my activation energy from this. Now I'm using the value in joules, not kilojoules. Vital you use the one in joules on this. That has gone in there over R, 8.31 times the T value, 300. Let's calculate all that. And by my reckoning, that comes to 30.4. One last thing to do though, that's the value of lna. To convert that into a, you can on your calculator just type shift ln answer. It's the easiest way. What you're actually doing is converting that into e to the 30.4. That will give you the value for a. It often comes out as a really large figure a. Don't be worried about that. There we go. All done. Bob's your uncle. That's how to get a. Now, some complex stuff that I've gone through. As I said a couple of times, the first part of it, justifying this rearrangement, is not strictly necessary for you to understand. Second part of it, completing a table, drawing a graph, calculating the gradient, calculating the value of the activation energy from that gradient, and finally calculating the value of A, you do need to be able to do. Now, it seems complex at first, I know, but with practice you'll be fine. I'll therefore set you a couple of questions. You're never going to get fully confident at this just by listening to me going on and on. You need to practice to gain full confidence. So it's really a matter now of tackling a couple of questions. So it's really a matter of just going back to this maths skills exercise I sent you the other day, in which you've already done questions 1 to 9, now doing the final question, question 10, to give you one practice at this. And then for a second practice, go back to the 5.1 question sheet, on which you should already have done up to the end of question 4. It leaves you with just one question left to do, which is indeed on this. Go ahead and do question 5 on that for a second bit of practice. Okay, long video this, with some complex stuff I know, but we're all done now. All the best with that. Look forward to seeing you all next week. Okay, bye now.